Welcome to the Deep Dive. Today we're diving into the world of classical and quantum computing. We've got some excerpts from the textbook Introduction to Classical and Quantum Computing to guide us, ready to unpack these complex concepts.
Absolutely. It's a journey from the familiar computers we use daily to the mind-boggling realm of quantum computers, which could revolutionize everything from medicine to material science.
So, Chapter 1 is Classical Information and Computation. To get us started, let's think about the evolution of computers. We began with humans doing calculations, hence the name computer. Then came mechanical calculators, massive computers with vacuum tubes, and now powerful computers in our pockets.
And despite these advancements, the core principle remains: the bit. The bit is the fundamental unit of information, a 0 or a 1. Like a light switch, it's on or off.
So the simple bit is behind all the complex things our devices do.
It is. What's amazing is how this abstract idea of a bit is physically represented in so many ways. Think about the tiny pits on a CD. They represent bits under a microscope. Even a coin toss, heads for 1, tails for 0. It's all about representing information in binary.
So how do we go from these zeros and ones to representing complex information like text or numbers?
By combining bits. Just like we use the decimal system with 10 digits, computers use binary with 2. With multiple bits, we can represent tons of information. For example, 8 bits give us 256 unique combinations, enough for all the letters, numbers, and symbols on a keyboard using ASCII code.
So my name, every word we're saying, this whole deep dive, it's all just bits to a computer.
Precisely. And these bits are manipulated by logic gates, the building blocks of computation. Imagine them as tiny switches controlling information flow, doing operations like A and D or R and not. These gates can be combined for more complex things like adding, subtracting, or even multiplying.
How do these logic gates become real in the physical world of computers?
That's where transistors come in. These microscopic switches, made from semiconductors, act as the physical logic gates. And thanks to Moore's law, the number of transistors on a chip has grown exponentially, making our devices incredibly powerful.
It's mind-blowing to think that billions of tiny switches are running our smartphones. It's like a city of microscopic workers, each with a simple job, but together doing incredible things.
And to manage these complex circuits, engineers use hardware description languages like Verilog. It's like writing code for the hardware, dictating how logic gates connect to perform specific functions.
But how do we make sense of these circuits with so many gates? It seems like it could get very confusing very quickly.
That's where Boolean algebra comes in. It's a mathematical framework to represent and simplify logic circuits. Using Boolean algebra, we can analyze and optimize complex circuits, making sure they do what they're supposed to. It's a powerful tool for understanding and manipulating logical operations.
So Boolean algebra is like the language of circuits, letting us express complex relationships between inputs and outputs in a clear way.
Exactly. It's amazing how this abstract mathematical concept is so crucial to the devices we use every day.
You mentioned reversible computing as a bridge between classical and quantum computing. What's that about?
Reversible computing means computations can run in reverse, so you can reconstruct the input from the output. Think of a movie you can play backward without losing any information.
That's interesting. How does it connect to quantum computing?
Quantum computers need reversible operations because they work differently than classical computers. In quantum mechanics, information can't be destroyed, so everything must be reversible.
So reversible computing sets the stage for the weird world of quantum computing. Before we cross over, let's talk about errors in classical computing. Devices are usually reliable, but errors do occur. How do we deal with that?
Error correction is vital. Even with billions of transistors, errors can happen due to noise or manufacturing flaws. To ensure reliability, classical computers use error correction techniques, adding extra bits to detect and correct errors. It's like a spell checker for computations, always looking for mistakes.
So even in the world of classical computing, we have to account for errors and uncertainty.
Absolutely. This focus on error correction is even more crucial in quantum computing, where qubits are very fragile.
Before we enter the quantum realm, there's one more thing from Chapter 1 that I'm curious about. Complexity classes. What are they and why should we care?
Complexity classes help us categorize problems based on how hard they are to compute. Think of it like classifying recipes based on cooking time. Some problems, like adding 2 numbers, are easy, while others, like factoring large numbers, can take forever, even for powerful computers.
So it's about understanding how inherently difficult different computational tasks are.
Exactly. And this leads to a fascinating unsolved problem, the P versus NP problem. It asks if every problem whose solution is easy to verify is also easy to solve.
So if we can easily check if an answer is right, does that mean finding that answer is also easy?
That's the big question. It's a puzzle that's been around for decades, and its solution could have major implications for fields like cryptography and artificial intelligence.
It's incredible how classifying the difficulty of problems can lead to such deep questions.
It shows the beauty of computer science and reminds us that even in advanced fields like computing, there are still mysteries to solve.
Okay, we've explored classical computing, from bits and logic gates to complexity classes and the P versus NP problem.
Okay.
Now, I'm ready for the quantum world. Chapter 2 introduces the qubit, the quantum bit. What makes a qubit different, and how does it challenge our classical intuitions?
Get ready for things to get strange. Unlike a classical bit, which can only be 0 or 1, a qubit can be in a superposition, being both 0 and 1 at the same time. Imagine a spinning coin, both heads and tails, until it lands.
Whoa, that's mind-bending. How do we visualize and understand this superposition?
We use the Bloch sphere. Picture a sphere where every point is a different quantum state. The north pole is 0, the south pole is 1, and every other point is a superposition of the two. It's a way to see the mix of 0 and 1 that a qubit can be.
So the Bloch sphere maps the quantum world, helping us navigate this weird superposition thing.
Exactly. It visually represents a qubit state and how different quantum operations affect it.
We talked about how bits can be things like coins or switches. What about a qubit? How do we physically make one?
There are a few different physical systems that can be a qubit. It's like a qubit zoo. Some popular ones are photons, particles of light that can be polarized in different directions, trapped ions, atoms held in place by electromagnetic fields, and superconducting circuits, tiny loops of wire that conduct electricity without resistance.
So multiple ways to create these quantum building blocks.
Yes. Each type of qubit has its pros and cons regarding stability, controllability, and scalability. It's a hot area of research, with scientists and engineers always pushing the limits.
It sounds like a race to build the best qubit. What are some of the challenges in creating and controlling these delicate quantum systems?
A major challenge is keeping qubits coherent. Decoherence is when qubits lose their quantum properties due to their environment. Like balancing a spinning coin on a vibrating table, the slightest disturbance messes things up.
So decoherence is the enemy of quantum computation, always threatening to disrupt those delicate qubits.
Precisely. And as we build bigger, more complex quantum computers, decoherence becomes even harder to fight. Overcoming it is key to unlocking the full potential of quantum computing.
Controlling these qubits sounds like a delicate art. How do we manipulate them to do computations?
Just like classical computers use logic gates to manipulate bits, quantum computers use quantum gates for qubits. But these quantum gates are different. They're represented by matrices, mathematical objects, and they transform the qubit state in specific ways.
So instead of simple A and D and OR switches, we have these matrices controlling the qubits. What are some of the important quantum gates?
A few stand out. The Pali gates, X, Y, and Z, rotate the qubit state around different axes on the Bloch sphere. Think of them as quantum flippers, changing the state from 0 to 1 or vice versa. Then there's the Hadamard gate, which creates superposition, turning a 0 or 1 into a blend of both. Like a quantum coin flip, it puts the qubit into a state of uncertainty.
So we can use these gates to precisely control a qubit, putting it into a superposition or flipping its state.
Exactly. Combining these gates in specific sequences creates complex quantum circuits that perform computations. It's like choreographing a quantum ballet, each qubit doing a precise dance to achieve a desired outcome.
Okay, I'm starting to grasp the power and complexity of quantum computation. We have these qubits that can be in superpositions, and we can manipulate them with quantum gates. What happens when we bring multiple qubits together? Chapter 4 is about multiple quantum bits. What new things can we do when we entangle these quantum building blocks?
That's where things get truly exciting. When we combine qubits, their state space grows exponentially. 2 qubits can be in a superposition of 4 states, 3 and 8, and so on.
So more qubits mean we can represent more complex information.
Exactly. This exponential growth gives quantum computers the potential to tackle problems that are impossible for classical computers. But it also makes representing and manipulating these multi-qubit states more challenging.
Okay, so how do we describe the state of multiple qubits mathematically? It seems like it could quickly become a jumbled mess.
We use the tensor product. It combines individual qubit states into one larger state that represents the whole system, like weaving threads into a tapestry. And this leads to one of the most mind-boggling things in quantum mechanics: entanglement.
Entanglement, we hear that word a lot. What does it mean, and why is it so special?
Entanglement is a purely quantum phenomenon where two or more qubits connect in a way that their fates are intertwined, even when physically separated. It's like having two coins linked, so if one lands on heads, the other instantly lands on tails, no matter how far apart they are.
Wow, that's strange. So it's not just that the two qubits are correlated. They're linked in a way that defies our normal understanding of space and time.
Exactly. Einstein called entanglement spooky action at a distance because it seemed to violate the idea that objects can only be influenced by their immediate surroundings. So entanglement really is mind-boggling. But how do we know it's not just some hidden classical correlation? How do we know this spooky action at a distance is real and not just some trick of the light?
That's a great question. It's easy to get lost in the weirdness of it all.
Scientists have come up with clever experiments to test quantum mechanics and rule out those classical explanations for entanglement. One of the most famous is the Bell test, named after physicist John Bell.
Bell test. Sounds kind of sci-fi, so how does it work?
Imagine two entangled particles sent to different locations. At each location, we measure the particle, randomly choosing from a set of possible measurements. If the particles were behaving classically, there would be limits on the correlations between the measurements, and those limits are described by Bell inequalities.
So these Bell inequalities set the boundaries for what's possible in a classical world.
Exactly, but the amazing thing is, quantum mechanics predicts that entangled particles can violate these Bell inequalities, and experiments, like Elaine Aspects in the 1980s, have confirmed these violations, proving entanglement is truly quantum and can't be explained by classical physics.
It's like quantum mechanics is saying, look, here's something your classical rules can't handle. It's amazing how experiments can push the boundaries of what we know and reveal the hidden workings of the universe.
Absolutely. The Bell test is a fantastic example of how theoretical predictions can be rigorously tested and confirmed. It's a cornerstone of modern physics and really changes how we understand reality.
Okay, so entanglement is real, and it's weird. But how can we use it for something practical? I'm curious to see how this spooky action at a distance can actually do something useful.
Entanglement is the basis for many exciting quantum protocols, leading to some groundbreaking applications. One that's really interesting is quantum teleportation. Now, this isn't about beaming objects like in Star Trek. It's about transferring quantum information between distant locations using entanglement. Imagine teleporting a quantum state, not physically moving it, but using that spooky link of entanglement.
Okay, now that sounds even weirder than entanglement itself.
Yeah.
How does quantum teleportation actually work?
Let's say Alice wants to send a qubit to Bob, who's far away. They share a pair of entangled qubits, one with Alice and one with Bob. Alice performs a joint measurement on her qubit and the entangled qubit and sends the classical result of this measurement to Bob. Then, using that classical information, Bob performs a specific operation on his entangled qubit, and boom! It becomes a replica of Alice's original qubit.
So the quantum information doesn't actually travel through space. It's like it disappears from Alice's qubit and reappears in Bob's, all thanks to entanglement. It's like a quantum magic trick.
Exactly. And it's important to remember that no information is traveling faster than light. The classical communication between Alice and Bob is still limited by the speed of light. But the entanglement lets them transfer quantum information without physically moving the qubit itself.
It's like entanglement creates a shortcut through space-time, so quantum information can jump between locations without actually traveling the distance.
That's a great way to think about it. Quantum teleportation has huge implications for quantum communication and quantum computing. It could lead to quantum networks that can securely transmit quantum information over long distances, creating a quantum internet.
A quantum internet. Now that sounds like science fiction. Secure communication that can't be eavesdropped on, distributed quantum computing where multiple computers work together, maybe even teleporting ourselves one day.
It's an exciting vision for the future. We're still in the early stages of developing quantum communication, but quantum teleportation is a key step towards making this quantum-connected world a reality. But let's not get ahead of ourselves. We have some technological hurdles to clear before we're teleporting ourselves.
Okay, fair enough. It seems like the deeper we go into the quantum realm, the more mind-blowing it gets. But before we get lost in the quantum future, let's talk about another practical use of entanglement: quantum key distribution.
Quantum key distribution, or QKD, is a method for secure communication that uses quantum mechanics to ensure the confidentiality and integrity of the information being transmitted. One well-known and widely used QKD scheme is the BB84 protocol.
So unbreakable codes, thanks to quantum mechanics. Sounds like something out of a spy movie.
Yeah.
How does this quantum cryptography work?
It's based on the fact that any attempt to measure a quantum system changes it. Imagine Alice wants to send a secret key to Bob. She encodes this key using a sequence of qubits, randomly choosing different polarization states for each one. Bob then measures these qubits, also randomly choosing its measurement basis.
So they're both playing a kind of quantum roulette with their encoding and measurement settings.
Precisely. And here's the key. If an eavesdropper, let's call her Eve, tries to intercept the qubits and measure them, her measurements will cause errors that Alice and Bob can detect. This tells them someone is eavesdropping, and they can discard any compromised keys.
So it's like Eve is trying to peek into a quantum safe, but the act of peeking sets off an alarm, alerting Alice and Bob. It's a really smart way to use the sensitivity of quantum systems to ensure secure communication.
Exactly. QKD offers a level of security that classical cryptography can't match. It shows how quantum mechanics isn't just a theoretical idea. It has real-world uses for improving our security and privacy in our interconnected world.
It's both fascinating and reassuring that we can use the strangeness of the quantum world to protect our information in the digital age. QKD is a great example of how quantum mechanics is more than just theory. It's a practical tool with real applications. We've covered the weirdness of entanglement, from how we know it's real, to its uses in quantum teleportation and quantum key distribution. Now, I'm excited to get to the heart of quantum computing, the algorithms that unlock the power of these quantum systems and solve problems in ways classical computers can't. Chapter 7 takes us to the world of quantum algorithms.